Right, this is Management 560, chapters 1 and 2. We're talking about just an introduction to the quantitative approach in general, now that we've done the data part of the class, and then we'll move on to some discussion of probabilities and how to manipulate them. So the quantitative analysis approach is discussed in chapter 1, and the basic idea here is to just think broadly about when we should be using mathematically based decision making and what are the advantages and disadvantages. So I've got a couple examples I'll talk about in class, but the basic idea is that if we use a scientific approach to decision making, we're seeking to collect data, to make conclusions, to try to generate models of the world. And so when we do that, it's very important that we get a couple things right. So first, it's important that we define the problem correctly, and this is probably the most critical aspect, in that it's very easy to be solving the wrong problem, and we can think of lots of examples of that. But conditional on solving the right problem, then it's an iterative process. So we develop a model of how we think the world works, and we acquire some data and check if it verifies our model. And if so, then we will develop a solution. So given our model of the world, we're going to have a best policy, and we'll implement it and then check if it worked. Get feedback in this form of new data and go back to the beginning. So define a new model then, and acquire data for that, and so on. So we're always updating our results. We're always updating our models. We're learning about the world. That's the scientific approach. And in business, it means updating our views of the world, changing our corporate policies or company policies or business policies to match our new information. And so the first step in that is understanding the basics of probability. So in this chapter, this is now chapter 2, we're going to talk about different types of probabilities and how to relate them to each other. So if I have a conditional probability, as I have here, probability of A given B, can I find the chance of, so if this is the chance of a Groupon going public, given that the economic times are really good, can I find out, can I use then a Groupon IPO to predict the future economic state, right? Can I turn things on its head, right? Can I recover joint probabilities from marginal and conditional probabilities, and so on. So we're talking about just a general skill set to take probabilistic information and express it in meaningful ways. And the simplest form of probability is an objective probability. So this is where we are taking, we have a big list of things that happened or possibilities, and we have a number of occurrences of a particular event, and the probability of that event is then the number of occurrences divided by the total number of opportunities that event had to occur. So it just very simply, how often did it happen divided by how often could it have happened, and that's the chance in any individual could it have happened that it would have. Simplest form of probability, and we can think of a quick couple business applications for this. So let's imagine that I've got a store, and the entrance to a store is just the space immediately behind the front doors is often called the decompression zone. If it's too busy, people passing the store will be hesitant to come in. So usually it's designed to be inviting. It's open, there's not a lot of merchandise in there, and the idea is you just sort of wander in and then just naturally flow into the looking at products, and then there's no obvious easy flow out. It's kind of like a fly trap. So we can think as a business, if we redesign our decompression zone, we want more people to come in and stay. And so the probability that people leave the decompression zone and enter the store divided by the total number that enter the store is an important statistic. Right? We want them to come in and then stay. And so we make sense to be tracking it. A clear example of occurrences versus trials, and you can think about every mile you drive on the road as a chance to get in an accident. But we can figure out the probability for overall for the United States of an accident per mile by just taking the total number of passenger miles driven and take the total number of accidents and divide that by it. And that would be the accident rate per mile. Now, obviously, it's going to be higher or lower depending on the driver, but we can get an overall statistic just using an objective probability. Generally, though, we won't have a whole bunch of opportunities to count up things, and so we may be making guesses, subjective guesses. And so that's where subjective probability comes in. So, for example, we might say if we had designed a small, I don't know, let's think all electric sports cars. Well, if we want to know the accident fraction for all electric sports cars, we probably won't have any data. There's just a handful of those right now. And so we would just instead be using subjective, right? So we might think, well, how often do sports cars get in accidents in general? Electrics tend to be peppier and also quieter. How do we think that will affect things? And essentially make an inference, a guess, an informed guess. Many probabilities in business are like that. So we have our logic, we have our experience, but because of situation specifics, we need to make an inference. And so often we start with these subjective probabilities, and then we might confirm them or adjust them as the data comes in. So that idea we can embody in the methods we'll do in this class, in this section, excuse me. Concepts and terms. So there are a couple different concepts we want to get our heads around. The first is the idea of event. So an event is something that has occurred in a set of events, is then a set of things that could occur. So if I've got a list of things that could happen, a mutually exclusive list is a set of events such that at most one of the set can occur. So if you think about, if I have one coin in my pocket, I can have a penny in my pocket, I can have a quarter in my pocket, and I can have a nickel in my pocket. And if there's only one coin in there, that means that at most one of those can happen, right? I can't have more than one of those happening. That means it's mutually exclusive. Notice what I just said is not collectively exhaustive. That's the second one. That's a set of events such that at least one must occur. And that's not true because I could have had a dime, right? I omitted that from the list, and it made it not collectively exhaustive. So I could add to my list. All right, so I've got a penny, I've got a quarter, I've got a nickel, I've got a dime, I've got gum, and I've got a dollar bill. So that's my new list. That list is collectively exhaustive because I said I have one coin in my pocket. So at least one of those things is going to happen. Is it mutually exclusive now? No. Why? Because I could have a nickel and gum. I said there was one coin, but there wasn't necessarily a limit on other things. So that set of events, penny, nickel, dime, quarter, gum, dollar bill, is collectively exhaustive but not mutually exclusive. Knowing which applies to a particular set of events is important because it will affect the probability formulas we use. So in terms of business, instead of coins in pockets, I could make a set of 3 events: Groupon having a successful IPO this year, Groupon not having a successful IPO this year, and Ford being profitable in the 4th quarter. Is this collectively exhaustive? Yes. Why? Because Groupon will either have a successful IPO or they won't. At least one of those has to happen. Is this set mutually exclusive? No. Why? Because Groupon can have a successful IPO and Ford can be profitable in quarter 4. Both can happen. So at most one occur is violated. The last concept is independent. So events are independent if knowing the outcome of one has no influence on your probability expectations for the other. So we often use dice and coins to think about this. And so if I flip a coin and I get heads, what's the chance I get heads? If I flip it again, well, still 1/2. The fact that we didn't use up a heads, or heads don't become less likely just because we used one up. Similarly, if you can think about flipping a coin and my breakfast. So certainly we would learn something about the world if we knew that I had cornflakes for breakfast, but it wouldn't affect the chance of getting a heads. So we would say that the probability of getting heads and the probability of me eating cornflakes are independent. They don't influence each other. The important thing here is that there are things that are related but not necessarily causally. So, for example, we might say that is the probability of me eating cornflakes for breakfast and the probability of me winning the lottery independent? And I would say the answer is no. Certainly, eating cornflakes can't cause me to win the lottery, but if I were a lottery winner, I might be having Eggs Benedict instead. And so the truth of the matter is that they're correlated, but they might not necessarily cause each other. This is especially true if there's an outside third cause that drives both. Marginal probabilities. Okay, 3 more terms. So we have basically 3 levels that we can think about probability. First, marginal probability, that's the chance that a particular event will occur. So it's a single event all by itself. That's marginal. Now, we can think about multiple events and stick them together. So we can say, well, what's the chance that I will get a heads on my coin and I will eat cornflakes? Well, that is not just one thing happening, right? So the chance I get heads is 1/2.